Here is the world's next 1,000-year power source, running in a shed in the middle of the Chinese desert at 2 megawatts, which is roughly enough to power about 2,000 American homes. Not a typo, not a rounding error, 2 megawatts. And yet people are calling this the reactor that could quietly start bleeding out the global oil industry. So either everybody is wildly overselling a science fair project, or we are watching the first 10 minutes of a story that ends with gas stations turning into charging lounges and petrostates renegotiating their entire economic identity. Let's find out which one it actually is. The golden fact here, the one nobody is talking about correctly, is this. The United States built this exact type of reactor first. Back in the 1960s at Oak Ridge National Laboratory in Tennessee, American engineers ran a molten salt reactor experiment that proved liquid fluoride fuel could work, that high temperature operation was survivable, and that you could shut the whole thing down safely just by draining it into a tank, like pulling a plug in a bathtub. Then the country walked away from it, not because it failed, because the uranium reactor program already had momentum, already had submarines, already had factories, already had regulators who understood it. The molten salt reactor did not lose on physics, it lost on logistics, on infrastructure, on the boring, unglamorous machinery of industrial scale-up. And now, more than half a century later, China picked that exact abandoned blueprint back up off the floor. That is the real headline. Not thorium magic, not some secret Chinese breakthrough nobody else could have found. It is a country with patience, state backing, and a 5-decade head start in hindsight, deciding to finish a project that America started and then shelved. So let's talk about what thorium actually is, because most of the internet gets this wrong in a way that matters. Thorium by itself is not fuel, not in the way uranium is fuel. Uranium, specifically a small slice of natural uranium, is what scientists call fissile, meaning you can hit it with a slow neutron and it will split apart right then and there, releasing energy and more neutrons to keep the chain reaction going. Thorium cannot do that on its own. It is what is called fertile. Think of it less like gasoline and more like crude oil before it has been refined. You cannot pour raw thorium into an engine and expect it to run. It has to be converted first, absorbing a neutron and going through a chain of transformations until it becomes uranium-233, which is the actual fissile material that can sustain a reaction. That means every thorium reactor needs a starter fuel, some initial fissile driver, usually uranium or plutonium, just to get the process moving in the first place. So the popular pitch that thorium simply replaces uranium and solves the fuel problem overnight is not quite honest. It is more accurate to say thorium extends and reshapes the fuel cycle rather than eliminating the need for it entirely. Here is the part that should genuinely surprise you though. Thorium and molten salt reactors are not actually the same thing, even though the internet talks about them like they are interchangeable. A molten salt reactor is a design, a way of building the machine, where the fuel is dissolved in hot liquid salt instead of packed into solid rods. You can run a molten salt reactor on uranium. You can run a solid fuel reactor on thorium. They are two separate technologies that happen to pair well together, and China is currently working on both halves at once, which is part of why this story is more complicated and more interesting than a single viral headline can capture. Translate that into car industry terms for a second, because that is the language this channel speaks. This is the equivalent of an automaker building a single hand-assembled prototype in a backlot, getting it to actually drive under its own power, and then announcing they successfully tested a new type of engine internally for the first time. It is real. It is a legitimate milestone. It is also very obviously nowhere close to a factory floor producing thousands of units a month. The distance between a working prototype and a profitable production line is where most ambitious technologies actually go to die, and everyone in this industry knows it. China's own stated roadmap admits as much. Their next target is a 100 megawatt thermal demonstration plant, aimed for around the year 2035. That is 50 times bigger than what exists today, and it is still not a commercial power station. It is still a demonstration. So if you are picturing gigawatt-scale thorium plants quietly replacing coal and gas across China within the next few years, pump the brakes. What actually exists right now is a research platform, extremely important as a proof of concept, but sitting at the very beginning of a very long industrial road. And that road is brutal. This is the part nobody puts in the highlight reel. Molten salt chemistry is aggressive. Fluoride salts can eat through metal over time if the chemistry inside is not controlled with extreme precision, which means the pipes, pumps, and heat exchangers all need exotic alloys that can survive high heat, radiation, and corrosion simultaneously, for years, without failing. Thorium specifically adds another headache on top of that. When thorium fuel is processed, the uranium-233 it produces comes bundled with uranium-232, a byproduct that emits strong gamma radiation. That makes the material harder and more expensive to handle safely, which is actually a silver lining for anyone worried about weapons proliferation, but a genuine engineering cost for anyone trying to build a commercial fuel cycle around it. Then there is the plumbing problem, and I mean that almost literally. In a molten salt design, the radioactive fuel is not locked inside a handful of solid rods sitting in one place. It is a liquid flowing continuously through pumps, valves, pipes, and processing equipment outside the core itself. Every one of those components becomes a place where things can go wrong, where salt can freeze and block a line, where seals can degrade, where remote maintenance becomes its own engineering discipline. America's own Nuclear Regulatory Commission has openly stated that there is no mature licensing framework yet for this style of reactor, limited real-world operating history to draw from, and unresolved questions about how to even properly test and qualify the fuel. In other words, even if China solves the physics, the paperwork, the safety case, the insurance, the decades of operational trust that a nuclear industry runs on, all of that still has to be built from scratch, on both sides of the Pacific. So now, the real question. If thorium finally works, at real scale, decades from now, does it actually put a dent in the oil industry the way the title promises? Here is where the story gets more interesting than a simple yes or no. Thorium reactors make electricity and heat. That is it. They do not produce gasoline, diesel, or jet fuel directly, because oil and electricity are not the same product competing in the same lane. So thorium cannot punch oil in the face directly. What it can do, if it ever becomes cheap and abundant enough, is strengthen the one lever that actually is already squeezing oil demand today, and that lever is electrification. Look at the numbers already in motion. In the United States, transportation eats up roughly 68% of all petroleum consumption, out of about 20.3 million barrels a day used across the country. That tells you something enormous. This was never primarily an electricity story. It was always, overwhelmingly, a transportation story. And globally, electric vehicles displaced more than 1.3 million barrels of oil demand per day in just the year 2024 alone, according to the International Energy Agency, with projections suggesting that number could climb toward 5.4 million barrels a day displaced by the end of this decade. That is not thorium. That is not even nuclear. That is simply electric cars, trucks, and buses already eating into oil's lunch, one commute at a time. So picture it as a chain reaction, pun fully intended. Cheap, reliable, always-on electricity leads to more electrification of vehicles, industry, and heating. More electrification leads to lower petroleum demand. Thorium's real role in that chain, if it ever gets there, is as one possible future source of that cheap, firm electricity, not as some direct oil-killing weapon on its own. It is infrastructure supporting a trend that is already happening, not a lightning bolt out of nowhere. And even in that optimistic future, some parts of the oil industry stay standing no matter what. Aviation fuel is brutally hard to replace with batteries because airplanes cannot afford to carry the weight. Long-distance shipping faces the same wall. Petrochemical feedstocks, the oil used to make plastics, lubricants, asphalt, and industrial materials, are not really an energy problem you can electrify away, because oil there is being used as raw chemical material, not as fuel. The International Energy Agency's own outlook actually expects global oil demand to plateau around 105.5 million barrels a day by 2030, not collapse, which tells you this is a slow bending of the curve, not a cliff. Now let's put the two countries side by side, the way you would compare two manufacturers fighting for the same market. China brings state-backed patience, a domestic manufacturing base that can build things at a pace few countries can match, and a willingness to fund a single technology for decades without demanding quarterly profits. The United States brings the original engineering blueprint from Oak Ridge, a deep bench of advanced nuclear startups, and a regulatory system that, while slower, has decades of credibility behind it. Companies like TerraPower are building sodium-cooled fast reactors with molten salt heat storage. X-Energy is working on high-temperature gas reactors using specially coated fuel particles. Kairos Power is testing fluoride salt-cooled systems and has already secured construction permits from American regulators. None of these American projects are thorium reactors specifically, which is an important distinction, but they represent the same underlying bet: that a new generation of nuclear technology can be smaller, safer, and more flexible than the giant plants of the past. So here's the provocative question worth sitting with for a second, the one worth arguing about in the comments. If China does eventually turn that 2 megawatt desert prototype into a genuinely commercial reactor before the United States commercializes its own advanced nuclear projects, does that actually matter for who wins the broader energy race? Or is the real prize simply whichever country builds the cheapest, most reliable electricity first, regardless of which specific reactor technology gets there? Because right now, thorium is not really competing against oil. It is competing against natural gas, against solar, against wind, against batteries, and against every other source of electricity, trying to prove it can be built cheap enough and fast enough to matter. Thorium has not won that competition yet. Nobody has. Not convincingly, not at the scale this story needs. What we actually know, cleanly, without the hype, is this. Thorium can be converted into usable nuclear fuel. That part is proven physics. Oak Ridge proved liquid fluoride reactors could technically run back in the 1960s. China is now operating a real, working, thorium-loaded molten salt research reactor and has reported evidence of that thorium actually converting as designed. What remains completely unproven is commercial thorium electricity, cheap thorium reactors, mass deployment at any real scale, and certainly any scenario where thorium single-handedly destroys the oil industry. The physics is not the obstacle anymore. The obstacle is everything boring that comes after the physics: the corrosion-resistant alloys, the licensing frameworks, the maintenance systems, the decades of operational trust that any energy technology needs before anyone lets it run their power grid. So no, thorium probably is not about destroying oil tomorrow, or even within the next decade. It is about whether the world can actually build a new source of cheap, firm electricity powerful enough to accelerate a shift that is already underway. One battery pack, one electrified truck fleet, one industrial furnace at a time. And if China does eventually manage to scale that 2 megawatt experiment into something commercially real, the question that will actually matter will not be whether thorium works in a laboratory in the Gansu desert. It will be whether an entire industrial economy can be rebuilt around it fast enough to change how the whole world burns, drives, and ships things, and whether America gets there first, gets there second, or gets there at all. For anyone who does not want to get blindsided by what happens next in this industry, whether it is battery technology, reactor technology, or whatever comes after both of them, join us here, because the garage of the future is being decided right now, in labs most people have never heard of.